Good morning, everybody. Welcome to this gentle walk through video over IP networks. And I'm going to talk about all aspects of video and how to get them over IP networks. I'll mention how to get them through studio networks, and I'll talk about how to get them through your own ISP networks, and I can talk about how to get them over the internet and into the home. Now, if we're going to talk about getting video over IP, you really need to understand what video is. Now, to do that, we're going to open up by talking about video and compression. Now, I'm sure you've often seen this diagram, or you can remember something like this in your physics lessons at school, and they're talking about light and how that white light is made up of our red, green, and blue components. And if you combine red, green, and blue completely together, you get white light. If you add red and green together, you get yellow, and you can get all these different shades by adding in various amounts of red, blue, and green. So with this system, it is an additive system. So we're adding light together to make different colors, and if we add them all together equally, we make up white. Now, just as a side issue, you may have seen this one here, which is your printer colors. Now, with printer colors, these are, so we use these in printers. Now, these are not additive, these are subtractive. Because you're starting with a white piece of paper. If you want to get black, you have to take away all the colors, so that if you subtract the cyan, the magenta, and the yellow, you'll end up with black. So with printers, they use a subtractive model, whereas if you're talking about videos and cameras or displays, we're using an additive model, because the default for the camera or the display is actually black, and we need to add in light to get it to white. Whereas printers, you're starting with white paper, so you have to take away to get black. Now, if we think about red, green, and blue, if we're measuring how much red light there is, how much green light there is, and how much blue light there is, then it's all digital, so we have to think, how many bits are we going to use to do our measurements? And if we were to measure using an 8-bit word, then that would give us, in each of our color measurements, 0 to 255 for our readings on the light that is going to make up our picture. Now, if we had maximum red, maximum green, and maximum blue, that will get us to white. Full blue, full green, full red gives us white. So there we'd get white. Now, if we have, say, 170 of red, 170 of green, and 0 of blue, that's red and green together, we're going to get yellow. So those readings would give us a nice yellow color. And we could have something like 0 there, 100 of green and blue, and we get that color there. Now, to get black, it would be 0 red, 0 green, and 0 blue. Now, this is if we're measuring the colors. If we turned that into just a pure measurement of how much light there is, then maximum reading on all colors would give us white. And then 0 on all the colors would give us black. Now, if we had 100 green, 100 blue, that adds up to 200. That gives us something like this. So you can see that if we measure how much red light and how much green light and how much blue light, we can actually display how much light in total there is, and this gives us our brightness or black and whiteness. So here you are on a desert island in the South Seas, and you've got a camera. Now, you're going to measure the light in that scene. You're standing there next to the beach, and you're going to measure the light. So you're going to measure the light, and you're going to just, let's concentrate on just a little bit of the scene there. And the camera is going to measure the light, and it's going to say, okay, we're going to measure a bit of how much red light is coming from there, and it's going to measure how much green light is coming from there, and it's going to measure how much blue light is coming from there. And all of that goes into the camera. Now, we know that red, green, and blue, when added all together, gives us the brightness. And so if I were to be displaying in black and white, and for those of you who are probably not as old to me, that seems crazy, but when I grew up, there was only black and white TV. So what they did was they had a camera, and this was a black and white camera, but what was it doing? It was measuring real light, and real light is made up of red, green, and blue. And then it totaled up the amount of light and generated a black and white picture, which was then sent down across some kind of medium and sent into the TV. Now that was simply a measure of what we might call, or what we do call, luminance, which is brightness. And luminance is the total of the red plus the green plus the blue. So we measure how much light there is in the picture, which is made up of red, green, and blue, and we total it up, and that can give us a black and white picture, because all we're interested in a black and white picture is how bright things are, whether they're black, white, or grey, or very grey, or something in between. So this is when we first started out with video cameras, and it was black and white, or what we would call monochrome. And this would be a black and white reading camera. Now, this is how I started watching TV, on black and white. So when they transmitted, and don't forget that, let me just insert a page here, that back in the days where video came from, there would be some kind of transmitter which would be transmitting through the air, and sitting at home, there would be somebody watching TV through a signal coming down a television aerial. Now, if they're sending me a black and white signal through the air, I'm very happy to receive it on my antenna, and it will go down and I'll watch black and white TV. And that was generally true in the 60s and 70s. And then people demanded more, and so color came along. Now, if we do think about color, there was a transition from black and white to color, and that wasn't overnight. So there was still me and my family, and we were still watching black and white. So we still had to receive the black and white signal. So the camera would send out a black and white signal, and the black and white signal would come to us, and we'd display it on our black and white TV. What about those people who were wealthy enough or forward-looking enough to watch a color? Well, if we think about color, what is color made of? Well, we said that color is made of red, green, and blue. But we're already sending them the black and white signal. If we're sending them the black and white signal, then that is made up of how much red, how much green, and how much blue. So I've no need to send them a black and white signal and an individual signal for red and green and blue. All I do is I send them, for those people watching color, they will also receive the black and white signal, and then they just add in the blue, and they add in the red, and they know that the black and white is the sum total of the blue and the red, so they can work out the green. So I've no need to send them a green signal. I can just send them the luminance, which is black and white, and the blue and the red, and they can work out the green themselves because they know that the luminance is the red, the green, and the blue. So if I send them the luminance, so if we say, okay, the luminance is equal to R plus G plus B, then if we just know the luminance, I take away the R and I take away the blue, I can work out the green for myself. So black and white TVs used luminance, but then the color TVs came along and we only sent them 2 extra signals because we had to keep sending the luminance for the people watching the black and white. Now, there were, back in the old days, things were analog, not digital, and they used to send signals. Here is the luminance. And then we've got the blue and the red. And they were sent separately, so if you're a black and white TV, you could ignore them. Now, this is in the old days, before it was digital. This was when we were sending analog signals over the radio waves, and it wasn't digital at all. Then we moved to digital. Now, when we move to digital, we get the luminance down here again. So this here is our digital signals. And when we've got our digital signals, we have the luminance. This is called the chrominance, and this will be the chrominance blue. So that's chrominance blue. And then we've got chrominance red. Now, what happens is when we are looking at pictures, if we see a picture which is very bright, or we see a picture that is very dark, our eyes really don't enjoy that. We like a nice balanced picture. And some of you might recognize this as kind of being called contrast. If the contrast is too low, we get dark. If it's too high, it gets very dark. If it's too low, it gets very flat. And we like our contrast to be very even. Now, when we think about the way that TV and the eye works, if we think about the way the eye works, then if we talk about perceived brightness, and then we look at amount of light, you might think that they're perfectly related. So if we did here 0.5, 1, here's 0.5, here's 1. If we double the amount of light, you'd think the eye would think it's twice as bright. But that's not true, because if you look at this reading here, this is how the human eye works. So this is called the human visual system. We send half the light, we can see that the perceived brightness there is 0.75. If we double the amount of light, then the perceived brightness is only 1. So doubling the amount of light, our eye doesn't think it's twice as bright. Whereas if you go to a low amount of light here, so if we go from, say, 0.25 to 0.5, we go from there to there, which is almost doubling the light. So our eye works in a very strange way, in that if you have very bright light and it's a bit more bright, our eye can't tell the difference. Whereas when it's working at low levels of light, if you light a candle in a dark room, it really illuminates it. Light a candle in a very bright room, you don't notice the difference. And we need to compensate for that working of the eye, and we call that compensation, when we're working with the eye, we call it gamma correction. So we can take a picture on our camera and we can gamma correct it. And so this here is high gamma, this is low gamma, and this is just perfect here, which is what the eye wants. Now, when we come back here, when we're talking about digital, you'll see Y for the luminance, but if you've got gamma corrected, and they've adjusted it to please the eye, they then don't call it luminance, they call it Luma, and then the chrominance becomes chroma. So we have chroma blue and we've got chroma red, and those are gamma corrected signals to make it so that our eye sees a lovely picture. Now you know that really when we're measuring, a camera is taking a picture, it uses pixels, and a pixel is just a point in space. So if we have this little array of pixels here, and if I want to give you a lovely picture for each little point in space, and each little point in space is called a pixel, that's just a point in the picture where we can make a measurement. So it's a measurement, is a pixel, and we want to see how much light is at that little point. Now, if I'm to give you a lovely, perfect picture at that point in space in the camera, I'm going to have to measure the luma, which is how bright it is. Now, if I want you to have a color picture, I'm going to have to measure the chroma red, and I'm going to have to measure the chroma blue. Now, I'm going to have to do that on every pixel. So I'm going to measure the luma for every point in that picture, and then I will measure the red for every point in that picture, and then I'm going to measure the blue for every point in that picture. So I've got 3 measurements per pixel. Now, the truth is that the eye is a wonderful piece of equipment, but it's not as sensitive to color as it is to brightness. So our eyes will see difference in brightness, but difference in color is not so good. So instead of doing 3 measurements for each pixel, I could be clever and go, okay, I know the eye is not so sensitive to color, so I'm going to measure the luma for every pixel, but I'm only going to measure the red, wrong color, that should be blue. I'm only going to measure the red and the blue on every other pixel. So now I'm not measuring the color on all pixels. And you can do this, and because the eye is not so sensitive to color, it won't notice the difference. So you can see, instead of having for each pixel 3 measurements, 3 measurements, 3 measurements, and if I add up, I've got to transmit those as a signal. And you can see I've got 1, 2, 3, 4, 5, 6, 7, 7 there. So that would be 21 pieces of data I have to send you. If I'm only doing 3, 1, 3, 1, 3, 1, and 1, then I've only got 4, 12, 13 pieces of data to send you. I've now cut down on the bandwidth. And when you're transmitting video, it's all about getting the bandwidth low, but keeping the human satisfied. So this is where we come into what we call Chroma Subsampling. So this is called Chroma Subsampling, and it means dropping out some of the color because the human eye won't notice. And it means if we're transmitting a signal over an IP network, we can keep the bandwidth lower because we don't have to transmit all that color information. Now, you often see, if you're configuring cameras or IP networks, that you might have to choose your signal. And you get 444, 422, 420, and combinations thereof. What does that mean? Well, that means that what we have is 4 samples of the luminance, the black and white, the Luma, 4 samples on both of those rows. When we come to read the color for those pixels, we do have 4 samples of color in the top pixels. So we've sampled color on each pixel, and we have 4 samples of color on the bottom row. So we've got luminance for every pixel, we've got color on every pixel. This is lossless full color. So we'd call this full color lossless. There's none gone. So when we combine the color with the luminance, we get our nice detailed colored picture, and you can see each pixel is a different color and a different brightness. Now, if we want to make that signal a little less, we could go to this one here. Now, this is the same. We do need the brightness on every pixel, so top and bottom row, 4 samples of brightness. The eye loves that and will detect it if you miss it out. But here on the top row, you can see we've only now got 2 samples of color. In the first pixel and the 4th pixel make up our 2 samples. Down below on the second row, we also have 2 samples of color. When we combine all our Luma with our Chroma, you can see that we put them together on the display as the individual pixels, and these 2 are the same color, blue, but they're of different brightness. So we accurately sampled the brightness, but we smudged the blue over the 2 pixels. These are green, these are red, these are purple. So that's 422. Now the last one that we're going to do here, this is going to be same again. We need all the brightness because the eye is very sensitive to that and we'll know it's missing. But here on the top row, we've got 2 samples of color, and on the bottom row, we've got 0 samples of color. So this is 420, and this actually is DVD quality video. So when you watch a DVD, you're watching 420. And I don't remember sitting next to people on a couch and them going, this DVD doesn't have enough color in it. So the human eye can be tricked, or not tricked, but is satisfied with less color than is actually in the scene. So you can see we've got blue, and we've smudged the blue over the 4 pixels there, and we've smudged the green over the 4 pixels there. So that's how video cameras record pictures. So for every pixel, they record the brightness and the blue and the red, and you can drop out some of the color when transmitting that signal to keep the bandwidth of the signal down. Now, if you work in a broadcast studio, somewhere like the Sky Studios or the BBC Studios or any broadcaster in the world, then you may have heard of SDI. Now, SDI is short for Serial Digital Interface. So it's a way of digitizing video, and you find this system used in professional studio environments. Now, how does SDI work? Well, here we've got cameras and we've got microphone, and we're going to have some kind of box, and you could connect your camera into these boxes. This is a great simplification if you do work in broadcast, I understand. And then out of the back of there, you could have an SDI signal going. Now, SDI, what it does, it uses this as a frame of a video picture. So you know that videos comprise of frames, 30 frames per second, 24 frames per second. One frame in SDI looks like this. And these here are the active pixels or the active samples. So this is what you actually see on the display. And then we've got something at the top, which is called a vertical blanking interval. And then we've got something down the side, which is horizontal blanking interval. Now, when we display it on the screen, that will be 1080 lines displayed on the screen, and each line will have in it 1920 pixels or samples. So this gives us our 1080, which is yours. 1080 is going to be your standard high definition TV. Sometimes you see it when you're changing channels. You may see 1080 come up into the corner of the screen, and that says that you're using 1080 lines by 1920. So all the pixels, if you multiply the two together, you get how many pixels are in your display. Now, due to the fact that in the old days we did watch TV like this, and these here were monochrome displays. This was a cathode ray tube, and that was a monochrome display. And the problem with that was we had to write lines like this on the display using a cathode ray. And when you got to the end of the line, you had to bring the little writing beam back to the beginning. And that took a little bit of time. And that was called your horizontal blanking interval, to let you get back to the beginning. So they, during that little time to get to the beginning, they didn't transmit anything. Likewise, when we got to the bottom, we had to come all the way back to the top for the next frame, and that was your vertical blanking interval. And so this is the origin of this. These are actually this is time in transmission, and that's the time it took to get your signal, your cathode ray, back to the top to write the new lines. Now, that is empty signal there. It's only these that are pixels that are truly displayed. Now we're still sending that bandwidth because of legacy networks. Now, what can we put in there? Well, that can be called we can put some data in there called the vertical ancillary data. We can put some data in here, and that's called your horizontal ancillary data. Now that's wasted space or wasted bandwidth. So what can we do? Well, we've got the video information. Why don't we take the audio and put the audio in this bit of time here? We can send the audio signal. We could also send subtitles during that empty bit of bandwidth. So the secret with SDI is that SDI is an embedded signal. And so with SDI, you have video plus audio. And you can stick in there subtitles and timing information and all kinds of stuff. And that's SDI. Now, if we think about our sampling rates for SDI, then we're going to end up with sampling rates like this. We're measuring color and luminance with 10 bits. If we're doing 13.5 megahertz at 10 bits, that's 135 megabits per second for the Luma. We've got the Chroma, blue and red, so we've got two of those. That's 270 megabits per second just for standard definition. High definition, you've got 1.5 gigabits per second for a high definition SDI signal. And that's too much to get into anybody watching this at home. So this is, I'll repeat, these are the type of signals you see within professional studios. If they're recording camera and audio high definition, you've got 1.5 gigabits per second just for your video. Now, just to go back, if you are doing fancy TVs, you could use 4K to get an even better picture. And 4K is going to give you 2160 lines by 3840. That's nearly 4000. So that's where you get your 4K from. If you're doing 8K video, then that's going to be 7680 pixels, and you're going to have 4320 lines. That's your 8K video. Now, if we are ending up with such high bandwidths, we have to do something if we're going to get it to the customer, if we're going to shove it over an IP network. So what do we do? Well, we need to do compression. Now, how do we do compression? Well, let's go back to our picture, and we've got lots of pixels in our picture. What we do is we take a block of those pixels. We've got 8 pixels by 8 pixels. Now that is now put into a block, and that's called a macro block. We take that macro block and we do a fancy mathematical transformation on it. And that's called, so we take that and we do a discrete cosine transformation. And what we get is now a macro block that looks like that. That's your DCT, your discrete cosine transformation. And you can already see that instead of having lots of different numbers to transmit, most of that is 0. So we don't need to transmit it. So we've now got less data to transmit. That means less bandwidth. So we've massively cut down on the bandwidth needed to transmit that macro block by sticking it in a fancy mathematical transformation. Now we can do those blocks all the way through that picture, can be split into blocks. We compress it using a discrete cosine transformation. Now my picture has taken up less data, it's easier to transmit. Now, all of that compression happened within the picture. So that is called intra-frame compression. So I took all the blocks and I compressed them down within that picture. It's intra-frame compression. And if I send you all those compressed blocks, you can recreate that picture because I've given you all information for that picture. And that's intra-compression. Now, if you imagine that that boat is actually moving through the picture to the left-hand side as we look at it, then is there any real need when it moves to transmit the same block again? Can't I just say, hey, remember that block in the last frame? Just move it to the side a little and repeat that block. So I don't need to transmit the whole block of information data again. I just send a vector moving the block around the picture. So what we can have here is this is a motion vector. So it means I don't have to retransmit the block. I just send a motion vector saying, hey, repeat from last frame. These blocks here, if the camera is not moving, they're not going to have changed at all. So there, I can just do something like, please repeat. So I no need to send that block in the next frame, I just repeat. And so you've got motion vectors pushing blocks around, and you've got repetition of previous blocks that you've already sent. And so we end up with our iframes. So we're going to have an iframe, and an iframe includes all information needed to recreate it. So all blocks are transmitted in an iframe. Then I've got a P frame. Now a P frame is a predictive. And all it does is it sends things like motion vectors, or it says repeat blocks compared to the iframe. So the P frame actually references the iframe. So once you've sent the iframe, you can send the P frame, and the P frame is just moving blocks around. So that there ends up in the P frame. It just says, oh, the same block, repeat it, and just send it across a bit. And we can have repeat blocks, which are just repeated with no motion at all. So the P frame references the iframe. Now the iframe contains all information needed to display that particular frame. The P frame doesn't have all information, it references the iframe. So the P frame will actually use less bandwidth than an iframe. So you can see I'm cutting my bandwidth down if I include P frames. And then we have the last type of frame, which is a B frame. And the B frame also does the same thing with motion vectors and repeat blocks. Who's it referencing? Well, B stands for bidirectional. So that can reference the P frame and it can reference the iframe. So just to repeat, the iframe is compressed, but it contains all information to display the frame. The P frame just references the iframe, and is really a list of changes. So we don't need to send so much information. But a P frame on its own is useless because it references the I frame. Now the B frame references the I frame or the B frame as it chooses. Now you can see we're cutting down the bandwidth needed to send the frames over the network because we're compressing in the I frame and we're referencing with the others. So you end up, when you're transmitting, you end up with this kind of situation. I frame, B, B, P, B, B, P, B, B, and then another I frame. Now, you can see that to get to another I frame, we've got I, 1, 2, 3, 4, 5, 6, 7, 8, 9 frames, and that is called our group of pictures. That is your GOP. And here we've got a 9 frame GOP before the next I frame comes in. Now, if we just go back to here, the P frame can only be built in reference to the I frame. If the third frame is a P frame, then we can only build it once we've got the I frame. So if this B frame, we want to build the B frame, we also have to have the P frame and the I frame. So if we go here and we say, okay, I'm going to send you an I, a B, and a P, really, you can't build any of the B's until the P has arrived. So although this here would be the display order, and so these are the frame numbers, frame number 1, frame number 2, frame number 3, frame number 4, that's the display order. If I'm going to help you to build the frames, then it's going to be better for me to send you the P frame before I send you the B frames, because the B frames actually reference the P. And so I'm going to send you the frames in this order to make it easier for you to rebuild the frames. So this is going to be the transmit order. So I'm going to transmit them, I, then the P, because you can build the P with reference to the I, and then you can use the B, and you can build the P, B with reference to the P and I. So the display order might be different to the transmit order. Now we talked about GOP length. So the group of pictures, and here our GOP length here is GOP equals 1, 2, 3, 4, 5, 6, 7, 8, 9. Does it matter how long your GOP length is? Well, yes, because if I'm transmitting, so we're transmitting up here, so you see the frames are coming in, arriving in this order. If I am watching a TV channel, if I want to change TV channels, so here I'm watching, maybe this is the BBC, this is BBC 1, and this is BBC 2, and this is ITV 1. If I'm making my BBC 1 with long GOPs, if I'm watching BBC 2 and I then want to change channel into another, I have to wait until the first I frame comes because everything references the I frame. So if you have long GOPs, it means if you're doing multi-stream transmission, your channel change will be longer, and people don't like waiting a few seconds for their channel to change. If you have a shorter GOP, if I'm watching one channel and I then want to suddenly change to watch another channel, the wait for the iframe to come in, which everything references, is short. So my channel change will be quick. So shorter GOP gives you a quicker channel change when you're transmitting multiple streams. Now, we've been talking about compression, and we've been talking about compression, and compression uses codecs. Now, here's a list of codecs. We've got H.264, and we've got a more advanced system, H.265. How do they differ? Well, H.265 gives us a greater variety of motion vectors. So that helps us with our compression. And we can vary the macro block size, which helps us with compression. So 264 gives us a lower bandwidth. You can see here for standard high definition, we've got around 3 megabits. If you're using 264, high definition 6 megabits. So different codecs, while using the same system of I-frames, P-frames, and B-frames, different codecs will give you different bandwidths because they compress more efficiently. Now, these Mpeg codecs, you have to pay licenses when you're building the encoders and decoders. So H.264 licensing very well understood, very much used. It's kind of an old standard now, but universal. Everybody supports it. 265, then you know the royalties and the payments aren't so certain. And then we've got open standards such as AV1, VP9, and you know Amazon, Netflix, Google. They're creating these open standards to get away from the Mpeg royalties that are needed. But H.264 is so old and so trusted, not old, but it's very well trusted and very well understood. So that's your universal codec. You've got other codecs that are available, but your equipment has to support it. So now we've talked about codecs, we might like to talk about containers, because we now need to get our stream over the network. And one of the common ways of getting a stream over a network is Mpeg Transport. So let's have a little chat about Mpeg Transport. So we've got our I-frames, our B-frames, and our P-frames. Now we need to get them over an IP network. So what we do is we give each of those frames, we give it a little header, and that's called the pairs header. And each of the frames has a little header so we know what kind of frame it is. Now this is called a packetized elementary stream, which is your pairs. Each frame has a pairs header to say what kind of frame it is, and we could take that packetized elementary stream and we could stick it straight on to a DVD. But we want to get it over an IP network. So we're going to have to take that packetized elementary stream. Now, the other way that you may transmit this would be in a very traditional manner, coming over your terrestrial digital TV over your TV aerial, and you can send that, and that would be called, if you sent that over the airwaves, which you can get DVB-T, which is digital video broadcast terrestrial, and we can take that and send it over transmission. Now, if we want to get that over an IP network, we're going to have to take all that and we're going to have to somehow get that onto the network card. And then it's going to go using something like Ethernet to get over the network. Now, if we're going to do that, we're going to have to use some kind of protocol stack, and that protocol stack is going to probably be using TCP, UDP, and IP. So we're going to end up with something like an Ethernet frame. Inside the Ethernet frame is going to be an IP packet. Inside the IP packet is going to be UDP datagram. Inside there is going to be RTP, and we've got to get that inside of there. So we've got RTP inside UDP, inside IP, inside Ethernet. Now, when we're thinking of putting our packetized elementary stream, and if we're going to put it inside of RTP, now what is RTP? RTP is used for live, often live audio and video transmission. It doesn't have to be live, but live audio and video transmission, RTP is our favorite protocol for that. There'll be an RTP header, and then there'll be UDP headers, and there'll be IP headers, and you'll have your Ethernet. Now, if we're going to get that inside of the RTP, then how are we going to do it? Well, that iframe, if it's a high definition iframe, yes, it's compressed, but it's going to be very large, and it might not fit in a complete IP packet, because don't forget, you're going to have an Ethernet restriction here. Your MTU is going to be 1500, so that means your IP packet has got to be 1500. Now, RTP, well, UDP, it's going to be 8, and that's going to be 12, so that's going to be 20. So you can see you've got to take off 40. So with RTP, you're going to end up here with 1460 to play with. How do we get them in? What we do is we take the iframe and we split it into lots of little pieces. Now, those little pieces, of which those little pieces, each one is 188 bytes, and those are our Mpeg transport stream packets. So we're now using Mpeg to get this over an IP network. 188 bytes, you will get 7 of them, which will give you 1316 bytes. And that fits nicely into RTP. So we get 7 of them into RTP, into UDP, into Ethernet, and off it goes. Now, we have to think, we've just talked about the video, we have to think about the audio as well. So here we've got the video. Let's add in the audio. And we've got to put that together into a single Mpeg transport stream. So we're now going to need, so let's just put the audio in. So the audio is going to go there. So we're going to need, whoever's reading that stream, we're going to have to tell them that that's audio and that's video. So how do we do that? Well, every one of your Mpeg transport stream packets has an Mpeg transport stream header. Now inside there, we can have an ID for the contents of that little transport stream packet. So you can see here, we've got 56 and 57. So we're now saying, okay, if you look inside the transport stream header, 56 is equal to the video, and 57 is equal to the audio. So now anybody receiving that stream can separate out the video and the audio for playback on the correct device. Now the truth is that we're going to have to, or we can, send multiple TV programs or TV channels together. Now, in this case here, for this TV channel, the top one, we've got 45 is the video. We've got 46 equals to the audio. And we've got 47, which we can add in there, and that can be subtitles. Then down here, we've got 56 equals video. 57 equals the audio. And 58 equals the subtitles. So now anybody receiving either of those streams knows how to decode the contents because they've been told through the IDs. Now, what we can do in reality is we can take those two TV video streams and we can stick them into a single Mpeg transport stream. So you can multiplex multiple channels into a single Mpeg transport stream. Now you can get, usually you can get 6, 8, 10 TV channels into a single Mpeg transport stream. So when you're distributing them through an IP network, you may only need one Mpeg transport stream to get multiple TV channels through your IP network. Now anybody receiving that transport stream needs to be able to pick out the TV channel that they want. So Mpeg transport streams, they love tables. And the tables tell you what's in the stream. So I can have the program association table, which here is the PAT. And that tells me how many different TV channels are in the stream. You can see I've got 3 here. And then I have an ID, let's say, so you could say, okay, we could label them and say, okay, so this is BBC 1, this is BBC 2, this is ITV 1. Now within each of those separate channels, there needs to be a program map table. So we've now got a PMT, and that's going to tell us, well, when you're looking at all those little transport stream packets, if you find the ones that are labeled 45, that's the video for BBC, ones labeled 46 are the audio, and 47 can be the subtitle. So now, if somebody is receiving that single stream, they can have a box that looks at that stream, and then it brings out the audio, it brings out the video, and it brings out the subtitles, and that's going to be given to the display. So over here, we've got some kind of display. That'll be a TV. All the other stuff can be just shunted away. Now, where does that go? Well, we could put it in the bin, or we could pick out another channel for recording to watch later. So if you've got PVR, something like that. So this is an Mpeg transport stream going over IP containing multiple TV channels, and it's the box that receives that will pull out the correct audio, video, and subtitles or data for the channel that you want to watch. Right, we've come to a natural break here. Let's have 5 or 10 minutes. Let's say it's 11:04, so let's come back at around 10 past, 12 minutes past, and we'll carry on from there. Just make yourself a cup of tea, have a loo break, and we'll come back in about 5 or 6, 7 minutes. Hello, let's carry on. Now, we did say earlier that we use compression to get things over networks. And if I can just remind you that we talked about iframes, bframes, and pframes, and we talked about macro blocks, and we talked about motion vectors. So what I'm going to do is I'm just going to show you, demonstrate that now to you using a piece of software called LINX Stream I. It's just an Mpeg analyzer. So I'm going to open up this MP4. Now you can see I've got audio and video in there, H.264 video. And so let's have a look. And this is 320 pixels by 240 pixels. It's super low definition, which is very easy for a demonstration. And I'm going to open up that. And here you can see stream type, H.264 codec, Chroma format 420. So we're Chroma Sub Sampling here, 420 that we talked about earlier. We talked about Chroma Sub Sampling 420, how we take all pixels have the luminance, the brightness, but we're only doing 2 samples of color. Now, if I just expand that up a little bit, here it's analyzing. You can see iframes, pframes, bframes. Now, if I start this running, that's an iframe, by the way, and you may see those come through the top. If I start this running, you can see that motion vectors, macro blocks, as this bear runs across the screen, you can see the motion vectors being displayed. So if we just pause it, and go back, let's run it again. So if we pause, you see there's a motion vector there that's just telling us to move the macro block. So this is a nice little demonstration of motion vectors, iframes, pframes, and bframes as we move through the video. All those big lines are motion vectors, and that shows us a nice little analysis of video compression using H.264. You can freely download. This is just a piece of demonstration software. There's other software that will do your analysis of MP4 files. And oh, there we go. So I'm just going to kill that now. So you've seen that. The other thing I'd just like to demonstrate is I'm going to open a transport stream analyzer. Now, we talked about the Mpeg transport streams, and we said that an Mpeg transport stream can have multiple TV programs or video channels in a single Mpeg transport stream. And we said that we need tables to be able to interpret all those different video channels in the Mpeg transport stream. And if I open up this little analyzer here, and I just come in here and go into the Mpeg transport stream, here's a multi-channel Mpeg transport stream, and here you see down here we have a list of all the programs which are the TV channels in this transport stream, and then some of the TV channels have video, audio, maybe 2 audios for stereo, and some of them have got subtitles. And each of these has a little ID called a PID, which is a program ID, so you know which transport packet, which little packet to pull out if you want the video. Now, I can also demonstrate that with a Wireshark, and with Wireshark I can open up a video, and that video is going to be this one here. I think it is. There it is. Now, we did say earlier that if we transmit, we're going to have, it's going to be UDP, and here it is. Here is the UDP. So if I filtered on UDP, here is my video in Wireshark, and that is UDP inside IP inside Ethernet. Now, we did say earlier that when we did do the RTP inside UDP inside IP, now Wireshark understands UDP, but why doesn't it tell us that it's RTP? Well, if we think about this, RTP is going to be transported inside UDP. Now, UDP has port numbers, so you may know common port numbers such as 53 for DNS, 67, 68 for DHCP. What's the port number for RTP? Well, there is no standard port number for RTP. So with RTP, if it goes inside UDP or TCP, there is no standard port number. No standard port number. So that means if you actually capture this in Wireshark, it doesn't know it's RTP because the UDP ports are unknown. But what I can do is I can right click, go to decode as, and here I can pull down and go to RTP and OK that. And all of a sudden, we now see that Wireshark can now, for each of these, Wireshark sees IP, UDP, but now it also sees the RTP. Now, when we're thinking about RTP, then it travels in UDP, no standard port number. Here is an RTP header. So if we look in Wireshark at the RTP header, what do we see inside it? Well, we see these fields, but this payload type is telling us what the RTP is carrying, and it is carrying an Mpeg transport stream. So when you look in the RTP header, there is the payload type, and that payload type indicates what we are carrying. So that is what is the payload type. Now, our example is 33 for an Mpeg transport stream. Now, there's sequence numbers. Now, these sequence numbers are just a record of the RTP packets. So those will increase 1 per RTP packet. And we can use that to sense loss, because if we have some missing sequence numbers on the receiver, we know we're getting drops. Now, this timestamp here, you may think, oh, well, that's the real time, 12:30 on the 1st of January. No, this timestamp is related to the codec clock. So if you were doing some kind of audio inside this stream, and that audio was running on, say, for example, the codec clock is 8,000 hertz, that would be 8,000 ticks per second. So that timestamp goes up by 8,000 every second. So that is a codec timestamp related to the running speed, sampling speed of the codec. Now, often contributing source, you don't see it because that's for conference calls, often not used. And this is just a random generated ID for the sender. So if we've got multiple streams coming in, we can identify which one this is. So going back to Wireshark, there you can see payload type, there's the sequence number 534. And if we were to look at the sequence number in the next one, it should be 535. And there it is. So it's going up 1 per packet. Now, we've got an Mpeg transport stream. And I do know that if we go down, we can see some things in here. And one of the things I'd like to see is let me just get my reference, packet 617. If we can go up to packet 617, I may be able to show you, here it is. Here's the program association table. So if we look inside there, here we see in the Mpeg transport stream the program association table. So here is the program association table saying that this stream actually has only one program in it. And then down below, there is the program map table saying that for this program number 1, if you pick out the little transport stream packets with the PID, the program identifier of 4D in hex, that's the audio. And we've got another audio channel, so it's obviously stereo. And then here, if you pick out all the little transport stream packets with 4F in the transport stream headers, then this is your video. So that's just demonstrating that you can see in Wireshark and analyzers what we talked about earlier. So this is RTP, used to carry audio and video. That's information that I've told you about before. And this is just from IANA, and you can see that 33 is indeed, if your eyes are that good, I can just expand this out a bit for you. But we looked at an example of 33, which is the recognized Mpeg Transport, Mpeg 2 transport streams. And you have some other codecs that are mapped here, but then the later numbers, you have to dynamically map the codec yourself. Right, so we've talked about compression, we've talked about video, we've talked about compression, we've talked about iframes, P frames, and B frames. How to get them over an IP network would be stick it in an Mpeg transport stream inside RTP, inside IP. So Mpeg 2 transport stream is an example of a container. So we can have an Mpeg, and that's an Mpeg 2 transport stream is an example of a container. And they will contain the audio and video which has been produced by a codec. So you could have inside your Mpeg 2 transport stream, you could have H.264 video, or you could have H.265 video. it doesn't matter. We're just using the Mpeg transport stream as a container to get it through the networks. It doesn't care what it carries and which codec you've used. So codec is different to container. Now, when you watch things at home, we're going to have certain problems if we want to get things to you. Now, one thing you may hear talked about is this thing called IPTV. IPTV. Now, IPTV is really where you control the network. Now, why do you need to control the network? Well, the reason is that if you are sitting at home, so you're sitting at home, you have some kind of box, and you're sitting there, you have a home router. But that home router is also a firewall. Now, if I wanted to send you a live stream, RTP, Mpeg Transport stream inside RTP, UDP, IP, then okay, we can imagine that we've got various routers around the place, and I'm going to have to send you that stream. Now, I could send you that stream inside UDP, RTP. Now, RTP has a port number. When it hits the firewall, why is the firewall going to let that stream in? And in fact, the firewall will block that because it is an unknown incoming stream. No unknown incoming traffic is allowed into your home network due to the actions of the firewall. So if I'm trying to get a video signal to you, I cannot use RTP, IP, UDP because your firewall will block it. Now, that's different if I control the network. If I control the network, then we have the situation of I control all the routers because I'm an internet service provider. I've also given you your home router, which is connected to some kind of set-top box. So here's our set-top box, which is connected into our TV. Now, if I'm the ISP and I control all of that, all the way up to the set-top box, because here is your home router, but I've provided that to you because I'm your ISP. Now, in that situation, I can get video using Mpeg transport streams inside RTP, inside UDP, inside IP. I can get that directly into your house to the set-top box. Why? Because I control the network. Whereas if I'm a content provider and I want to get it to you in your home, unless I control the network, I can't get it through your firewall. So IPTV is usually direct video to set-top box through our own network, because then I have no problems at all with firewalls, and that's IPTV. So if you are BT, you've got BT broadband, you've got a BT set-top box, it's all BT, they can use the methods I've told you so far for getting their sports channels right up to your TV. Now, this isn't going to be the case if you're using something like Netflix. Netflix don't control your network, and they can't open ports on the outside of your firewall to get their TV videos, movies into your home. So this is where OTT and ABR comes in. Now, what's happening here is we've got you're sitting at home, and you will have your firewall there. So there's your firewall, and you're sitting some kind of video box, and you're sitting there in front of it. That's connected there, which is connected out to some kind of network. And then how do you go to Netflix to get their movies? Well, you make the connection out. Because you've made the connection out, the reply is now able to come in because your firewall has seen the connection go out and will let the reply come in. So you have to ask for the video, and that is an outgoing connection. Because it's an outgoing connection, your firewall doesn't have a problem in allowing the video to come back in. So as opposed to IPTV, where it was initiated and forced from the outside, when we're doing OTT, we initiate from the inside, the video is then allowed to come in, and we call this over the top. This is over the top, and it's over the top of our favorite protocol, HTTP. Now, why HTTP? Because firewalls have no problem. They're used to HTTP, and they don't have a problem letting the replies in. So if we can do it all over HTTP, then we don't have any problems with the firewalls. So when you're watching videos on catch-up, on demand, Netflix, BBC iPlayer, it's all done over HTTP because you don't get any of the problems. Now, this here is going to be HTTP. Now, HTTP, you know, will use TCP, not UDP. And we like that because with TCP, you can have a device that, so here's your device watching TV, and built into that is going to be some kind of decoder, and that's built into there. We've got our decoder to receive the stream, and inside there we're going to have a TCP incoming buffer. Now that TCP incoming buffer allows me, when the HTTP streams in, I can store it for a short time in the TCP buffer, because if you're then suffering some kind of packet drop, then TCP can actually request a resend of missing data. So that means that when we do play the video out, it plays out wonderfully with no mistakes because we had an incoming buffer. And that's great because we're using TCP. And TCP can fill in the missing pieces because TCP is reliable and you can get a resend. So that's OTT, over the top, getting video into people's homes over HTTP because we have no problems with the firewall. TCP gives us the possibility of asking for resends if we get a packet dropped. Now, that's the OTT bit. What about the ABR bit? Well, ABR is adaptive bitrate. Now, adaptive bitrate means you can change the quality of the video download according if network conditions change. So if your network is not performing well, you can go to a lower standard of quality. So you can start out watching your 4K video. Then if we get a lot of network congestion, we can then just change to go down to 720. We still watch the movie. I'm still satisfied in that I haven't lost the movie, but there might be a lesser quality. So it's adaptive bitrate. The quality of the video changes according to the network conditions. Now, how is it all done? Well, you know that we have our stream of frames. We have compressed the stream of frames. So we have our, what we talked about earlier, we have our GOP here, which is our group of pictures. We said you don't want your GOPs too long, because that means if you're changing between streams, you have to wait for the next iframe to come in. So what do? We take our movie and we decide what our GOP length should be. So this is a short GOP, and a short GOP means easy to change streams. If we have a long GOP, not so easy when I'm trying to change channels or change streams. So if I take a movie that I wish to send you and I split it into segments. So these things here are, this is a segment. Now notice at the beginning, there is always, at the beginning of a segment, there is always an iframe, because we need that reference when building the P frames and the B frames. So there's always an iframe at the beginning of your segments. Now I can take the movie and I can take one single movie and I can split it into segments, and I have each segment at different definitions. So we could have this here could be low quality. This here is very high quality. So the low quality segment doesn't take up much bandwidth. The high quality segment will take up a lot more bandwidth. I take a single movie, so each of these is the stream required for a single movie. So I've taken a movie and I've split it into segments, and that whole movie is split up into segments for different qualities. So I have actually now got 4 copies of the movie, all at different qualities. What can I do? I can start streaming. So I start streaming and I'll set off at a medium quality. So here I am, I start my streaming medium quality. I download that segment. It downloads so quickly, I have time to spare. So I think, oh, wow, the network's really good. Why don't I, when the segment ends, change to a higher quality video? So I can then change up to a higher definition and I can stream that. And if that downloads nicely, I'll carry on, and I may even, if the network conditions allow, change to the highest quality available to me. Now, network conditions can change. So while we're downloading one of the segments, we can realize that the speed of my network is slowing down. So I can say, okay, for the next segment, I'm going to go down in quality and stream out, play out a different quality. And you can go down to really poor quality for your playout. Now this means that the quality of the video I'm watching does change, but hey, I'm still watching the movie. And what do people want? Do they want us to stop the movie and then have a big download wait? Or do people want to carry on watching? They want to carry on watching. So this is why when you watch iPlayer, BBC iPlayer or Netflix, it may start out at a little lower quality and then all of a sudden, bang, it goes clear. This is your adaptive bitrate. Now, not everybody's doing everything the same. So we've got HLS, which is adaptive bitrate, but this is for Apple. You've got Microsoft Smooth Streaming, so they do it a different way. And you've got Mpeg-, which is the open standard. Now, which one of those you use depends upon the device that you're trying to download from. Now, the problem is it's are available to me. When I start the movie, where do I know to get these segments from? And how do I know what kind of segments are available to me? Well, with Mpeg-, there is a file that you can download right at the beginning, and that's called an MPD file. With HLS, it is an M3U8 file. And these are called the manifest files. And they say what bit rates, what's available, and where you are, how you're going to stream them. Now, here's an example of a manifest file. You can see that in here we've got lots of information. I'm not going to explain all of this, but what I can say is that, okay, look at this. That says we have got 30 ticks per second. Really, we're transmitting at a frame rate of 30. So that is 30 ticks, frames per second. Each segment is 120 ticks. So if we've got 120 ticks for each segment is 4 seconds long. You can see I've got available they're all frame rate of 30, but I've got different picture aspect ratios. There's 1024, there's 1080 by 1920. Here, oh look, we've got a lovely 4K up there. So that's the manifest file that's used to tell me what's available and where to go and get them. It gives me a URL. That's the base URL, which means, okay, wherever you are now. So I could be somewhere like http://rob.com. So that's my base URL. and then representation ID. So then I put this up here, and then I add on representation ID with .m4v and the number of the segment that I want. So I do build up a URL of where to get the segments from. So that's an MPD file. So what's happening is you do have some kind, so this is the workflow from camera all the way to screen. You've got a camera pumping out SDI. So that will go in the studio, and that's going to be something like SDI. That goes out to the television company. They will then play out. So it goes to play out. So this is play out, and that's going to be maybe an Mpeg Transport stream. So you've got an Mpeg Transport stream at play out. Then we may be using some kind of content delivery network, and this is our origin server and the content delivery network. We play out to the origin, and then if somebody using Mpeg Dash, an Android phone, connects in to the edge server in our content delivery network, they will request for the segments to be downloaded, and I'll play out the segments on my device. So we've got Mpeg Dash, Open, HLS, Apple, Microsoft Smooth Streaming. That's the Microsoft method of this OTT, adaptive bitrate. And the last thing I want to show you is that this can all be done live with a single device. So you can have a single device that's sitting there, and you can have your smart TV request the movie in Mpeg Dash. You could have an Apple TV request the movie in HLS. You could have some kind of Xbox Live request the movie in Smooth, and a single device will automatically on the fly create the segments, create the manifests, and stream it all out to you. And this is what's happening when you're sitting at home watching TV on Netflix or BBC iPlayer. It's all OTT ABR. And just as a last thing to show you, Akamai will show you, has this little experimental or test player. So this is a Dash player, dynamic adaptive streaming over HTTP. This is the open standard. If I just load that up, we're going to stream a movie using OTT ABR Dash. And look at the resolution, 480 by 270. Boom, it just changed. 3840, I've gone up to 4K. And if we look downstairs, you can see my buffer level and my video rate. And you want the buffer to be more, really, or you want the buffer to be more than the video rate. And you can see we're moving along slightly, but I've gone down to 1920. So I was network conditions not so good for 4K. Oh, it's just changed again up to 4K. So I'm wandering around the segments as I stream. I'm wandering around the segments trying to get the best experience possible using ABR OTT. And that's where I'm going to stop it now. And I'm going to say thank you for listening to me. I hope you enjoyed that. And I hope you now have a little understanding of how video works, how we get video through IP networks, Mpeg Transport streams. But to get it into your home, I'm going to do OTT ABR, so you can watch Netflix and Apple TV and Prime all in the highest quality. So I'll hand it back to Holly, if you're there, Holly.
I am, perfect. Thank you very much, Rob. So a few questions. If you do have any questions for Rob or myself or any of the LINX team, just remember to use the Q&A function down below, and we'll get back to you. So first question, if the iframe contains the full frame and the P and B frames are based on this, what happens if the new content rather than moved content needs to be displayed in between iframes?
You can't. You can't. If you're what you're referring to is this here, where we talked about channel changing here. So if you do change channel, you have to wait for the iframe to come in. So that's why there is a delay sometimes when changing channels when watching these kinds of services. But hopefully they keep the GOP nice and short, so you get a quick response. You have to have the iframe and wait for it to come in. Now there are tricksy ways to get around this. Your set-top box could actually be buffering up other channels, so that what they can do is when you change the channel, they won't display the channel immediately because they wait for the iframe. So they'll buffer up, wait for the iframe, and then they'll only change the channel when the iframe comes in. So it looks to you as if it's a crisp change, but in fact they just played your old channel out a bit until the iframe on the new channel came in. You've got to have the iframe.
Lovely, thank you. And then just to let you all know, this is being recorded and will be available on demand afterwards on our Learn with LINX webpage. I've added the link in the chat. But we haven't got any more questions come through just yet, so I'll just finish off by thanking you all for joining us. We hope you enjoyed this session, and remember, if you have any other webinar topic suggestions, if you could please get back to us on that. And remember, there will be a short survey after you leave the webinar, and we'd really appreciate it if you could just give us a minute of your time and tell us your thoughts. Both myself and Rob will stay on the call for an extra few minutes for any last minute questions you have, but if not, thank you very much for attending, and we hope to see you for our next webinars.
So you're an expert in video now, Holly?
I am, and I very much appreciated your drawings of the houses and the TVs in the houses.
A little primitive.
Making.
A little primitive. It's kind of, can you guess what it is yet? But, or guess at all what it is. So,
yeah.
But, it's nice to get drawings in real time. It gives it engages a bit more.
Yeah. Right, Rob, we have another question for you. Thank you, Gareth. I think the previous person was asking what happens if a new item comes into the frame, i.e. a P frame after prediction is there, an additional compression of the remaining difference between the predicted result and the frame being encoded?
Can you repeat that question?
Of course. So I think the previous person was asking what happens if a new item comes into the frame, i.e. in a P frame after...
Okay. If we go back to, I think, where we talked here. Now, if a new item comes into the frame, if something new whizzes in, or we're doing a P frame and something new whizzes into the frame, then we need to transmit that as a pure new block of new information. So the P frame isn't solely references to the I frame, it can contain new information, and so can a B frame. But we would like to reference the I frame because it means we cut down on the amount of data that's sent. So you can have new items, new pixels, new macro blocks in the P-frame, but we just like to reference the iframe because it's gives us our compression and cut down on the bandwidth. So you can have completely new information in the P-frame and the B-frame. Doesn't have to be only references to the iframe.
Gareth, does that answer your question? It does, perfect, thank you. And just for everyone still on the call, I'm just going to add some links into the chat. So you've got our future events, which we've got a few more webinars with S&T coming up, the webinar recordings page, and then if you need to contact us about anything. But I think with that, we will end the webinar. So thank you very much, Rob, for training us all today. And thank you everyone still on the line. We hope you have a lovely rest of your day. Thank you very much.
Thank you.